Hello, I'm Luca di Persio. I'm the scientific coordinator of the master degree in data science at the University of Verona. And today I would like to introduce you Professor Paolo Dai Pra, who will speak about one of the three fundamental courses within the first year of the master degree, which is probability for data science. In particular, Professor Paolo Dai Pra will speak about the main aims and scopes of the course itself. So I strongly hope you will enjoy his presentation, and I also hope to see you in Verona soon. Thanks for your attention, and bye.
Hello, everyone. This is a short presentation of one of the core courses of the master degree in data science, and the course name is Probability for Data Science. So before giving you some details of this course, I'm going to try to answer to the most natural question: why probability for a data scientist? Well, it is actually widely accepted that probability is a must-know concept for data scientists at all levels. And the reason, in a sense, is simple, because when you do data analysis, essentially in all steps of data analysis, from data sources to prediction of unobserved data, then you cannot avoid uncertainty. Uncertainty is always there, and it matters. So this means that deterministic models are typically unrealistic in this context. And so you have to rely on models in which you have some randomness, some stochasticity. And probability is the mathematics that allows to do that. So to sound a little more convincing than that, let me mention a couple of examples. So the first example is a sort of typical problem in artificial intelligence and machine learning. So it's image recognition. So you have an image, maybe a picture or a dynamical image like a video, and there are individuals that appear in this image, and you want to write an algorithm that determines automatically some features of these individuals. For example, sex, age, maybe the mood. This is a very hard task, but machine learning can do that in a way that in certain circumstances is really unbelievable. But what exactly it means to solve a problem like that? Well, it means essentially to determine an input-output map. So you have an input, you have your input, X, which is your image. An image is coded, you have pixels, and for each pixel you have a color level, so you can imagine how to code an image. Then you have an output, which is what you want to know, the features of the individuals. And what you want to determine is a relation between X and Y that is going to be used for prediction. Because when you have a prediction problem, you know X, you want to know Y. So you want to establish a relation between X and Y, a link between X and Y. And ideally this link could be just a function. If I give you X, I apply this function to X and I get Y. Well, this is typically unrealistic. There is no way of making 100% sure predictions in a context like this. So you must allow some randomness, some disturbance. And so you should consider models of the following type, for which Y, your output Y, is a function of your input X and of some other variable W, which is a random object that is going to describe the uncertainty of your prediction. So for example, given X, what is the probability of having a given value of Y? So in this way, if you give a model like that, you can also, for example, make estimates of what is the probability of making an error in your prediction, or predicting wrong features for individuals. So it is very useful to have a model like that, despite it is a probabilistic model and is not a deterministic model. Of course, I mean, to formulate a model like that, you need probability. Then if you really want to determine a model like that, then you need statistics, you need machine learning. Typically, you would like to construct a model, so a function f, a function of the input and of the disturbance w, that, for example, makes the disturbance as small as possible, so the randomness is not too big. So you have a rather reliable prediction. And in order to do that, you need examples, you need data. So you need essentially to have a lot of pictures for which you know what is the right answer, the right value of y. So this is a so-called training set. And by using the training set, you can determine a good model for your future predictions. Another example I would like to mention is a kind of dynamical examples in which your problem, your data is the evolution in time, for example, of the price of a given asset in a financial market. So you can imagine you have data that you can plot and you get a picture like this. So at any time t, you have the price of your asset. You can imagine the time is discrete. So for example, the prices are recorded daily. Here, what you would like to build is a dynamical model. So if I know the prices of my asset up to today, can I predict the price tomorrow or the day after tomorrow, or in general in some future time? Well, the simplest type of dynamical model one can consider is are models of this form, in which the price at time t+1 is equal to a function of the price at time t, and of course of some disturbance. This also in this application you cannot even conceive a deterministic model. If price prediction were deterministic, then I mean probably there would be no market at all. So this is now a dynamical model. So it's a model that describes an evolution. Again, the variable w, that is not a single variable because you have one w for every t, accounts for the uncertainty of the change of price from time t to time t+1. Now, the aim of this probability course is to provide models for these and other applications. And on one hand, we will introduce the models in a mathematically rigorous way. So there are going to be theorems and proofs, but also we are going to have to see applications, case studies, and so we are going to go in the lab to program and really to do a real data analysis on real data, typically using Python or R as programming languages. So let us give a look at the course content. So we're going to start from the very beginning, so from the notion of probability, of conditional probability independence. We're going to talk about random variables and their distribution. So this is something that many of the students may have already heard of. But then we are going to go into sort of aspects of probability that are more relevant for data science. For example, we're going to see high-dimensional random variables that are the right mathematics to model big data. So we're going to prove limit theorems and their applications. Then, as I already mentioned, we are going to see dynamical models. For example, Markov chains, counting processes, renewal processes, queuing models. And we are also going to see some computational aspects. For example, Markov chains, besides being good models for time evolution, can also be used at a computational level to solve hard computational problems. And this is a very interesting theory that typically is referred with the name of Markov chain Monte Carlo. So this is more or less all I wanted to say. If you want, if you have questions, you want more infos, you can contact either myself, I am Paolo Dai Pra, or my colleague Luca di Persio. And I hope to see you in Verona, and thanks a lot for your attention.